right, awesome. So this is season 4, episode 1, and I'm Fadikemi, and with me is Ayo.
Hi.
Okay, so in this episode, we'll be talking about Dynamo. So here's like a prelude I have to the episode, just to kind of set the context. So Dynamo is a system made by Amazon. And so let's imagine that it's Black Friday at Amazon, and like millions of people are adding to cart at the same time, trying to get like the best deals of everything. So it's like a quickest fingers kind of thing going on because Black Friday is just one day. So in such a scenario, like if the database should hiccup for even a second, cards could vanish, customers could leave like the platform because if their cards suddenly become empty, they will be annoyed and leave. And so this actually has like financial implications to the business
Mhm.
because the point is that if I add to carts, it better have been added to carts. And if I want to view my cards, you better have something to show me. And
Yep.
so in such a situation, how do you build a database that just never goes down? So this
Mhm.
was the problem that Amazon engineers faced back in the 2000s. This was before like NoSQL databases were a thing. And so in such a time, they were able to think about a system like Dynamo. So in this episode of Sys Design Conversations, we'll be exploring the 2007 paper that reshaped how we think about distributed databases and inspired the NoSQL movement. It's titled Dynamo, Amazon's highly available key value store. So yeah, really excited for this one.
Yes, very excited. A lot of interesting things were spoken about in the paper. So, yes, we're excited.
Mm-hmm. Yep. All right, so let's get into the episode. I think the first thing to address is what even is Dynamo. Yeah.
Yeah, I think it's like you just said. So Amazon needed to build a system because they had certain availability slash reliability requirements that traditional data stores didn't provide. And so Dynamo is a system they built for that. It's a key value store that is highly available and it is labeled as an always on system, which means that it never rejects a write. But like
Mhm.
this is what I understand from that. So it never rejects a write and it always handles the so it not rejecting a write means that it is um there's like a cost for that. So in traditional databases, consistency is really important, and sometimes, at the expense of availability, these traditional databases, relational ones, will um, have like reduced availability. So Dynamo, to have the level of availability it needed, especially in situations where things were broken, it needed to compromise on consistency. Which means so it didn't introduce the concept of eventual consistency, but this was used a lot in Dynamo.
Mhm.
Yeah.
Yep. Yeah. So yeah, so Dynamo is like a storage system that they used as compared to like using like a relational DB.
Yeah. It's kind of important to note though that Dynamo it didn't replace all usage of all databases for Amazon. Amazon had a select few systems that didn't really need the what relational databases offered, right? So relational databases provide you the relational schema, they provide you like complex queries, semantics that you can use to join things and fetch things and analyze things. And for some of the systems, they just needed to get data based on a key and that was it.
Mm-hmm.
So stuff like session management, when a user is logged in, and you want like the session to be persistent, you want to know if they're still logged in, and so on and so forth. Um, the shopping cart was a big topic in the paper.
Mm-hmm.
When a user is, adding to cart and removing from cart, a lot of those are just like key value semantics. And there were some other things like product catalog. So if I want to fetch like a product catalog, I just need to fetch it by the key and display like the list of product. So there were a few like scenarios where they didn't need the like all of the functionalities that relational database provided,
Mm-hmm.
and so Dynamo was built to for this situation. So it didn't replace all use cases, but it did replace some of them.
Yeah. I think like particularly use cases where um the users like where availability was more important than like correctness of the data. So like the shopping cart example you made, when you're on an e-commerce platform, I think most users would prefer that maybe their shopping cart is not as up to date or is slightly stale than for it to be down, like for it
Yeah,
to not show any data. So yeah,
yeah,
I guess
yeah.
in such like scenarios, it was more important that the system was available than for it to be like accurate.
Yeah, like
Uh,
think about being on Amazon and like trying to add to cart and it's like, oh, try again in like 5 minutes or
yeah,
something.
like I'm going to leave and not come back.
Yeah, and this is really important because these like decisions have financial implications.
Mhm,
And this is really important for Amazon, like especially if you're an e-commerce site. The card is probably like the most important thing. It's kind of the step
mhm,
right before people buy things.
mhm.
And if anything there has a hiccup, yeah, people are probably not going to buy it. So
Yep,
yeah.
yeah. So yeah, I definitely think that was the what they had in mind when they thought of Dynamo. Okay, so let's try to like tackle the core ideas of Dynamo. Dynamo
Mhm,
at the time it was written, I feel like it's pushed the boundaries of like course site reliability concepts like
mhm,
consistency versus availability, durability versus performance. These were things that like I think maybe before then there wasn't much thought about trading off one for the other. It was
mhm,
just kind of like, I mean, the CAP theorem existed where like consistency, availability, and like partition tolerance were like things that you can have all three at a time. But there was also like an extent to which you could have one and not have the other. I think they were able to like play with that a lot and like extend the capabilities of what they could achieve like within those concepts. So it was really
yeah.
interesting.
I think something that was really special about the paper was, um, at least for me, was the combination of things that they put in place to achieve what they wanted to achieve.
Mhm,
I don't know that at least it's not very clear to me anyway, that they built something new. Like any of the things that they used was like new. Like I don't know that that's the case. It's possible, but maybe I missed it. But I do think that what the innovation is from like my point of view is just how they combined all of these things to like at the end of the paper, it just goes on and tells us that Dynamo was available for like 5 nines and it never lost any data over 2 years. So whatever they want to tell us, I want to hear because, if like whatever you have built has resulted in this type of system performance or this level of performance for your product, then is worth hearing. So I think that the innovation was just how everything was combined um to achieve what they wanted to achieve. So
mhm.
yes, in
Yeah, definitely. So Dynamo is a distributed storage system, right?
mhm,
And so to the main point of it being distributed is that like data is stored on different nodes, right? So, and these nodes like kind of all work together. So we
hmm
can talk about like partitioning first, since that's like related,
hmm
and yeah, see how it does this.
So I want to make like a small distinction. So a distributed system is, as long as you have, I don't know like a formal definition. There's probably a formal definition elsewhere. But as long as you have multiple nodes that are communicating one another to kind of achieve something, I think you have a distributed system. And I think it's possible to have a distributed system without having it like use partition, for example, partitioning, for example. So I wanted to like make that small distinction. So
Okay.
for partitioning, the so the way that Dynamo achieved partitioning was through something called consistent hashing. And consistent hashing like itself wasn't new, and it was kind of an improvement of the way requests used to be routed to servers previously. And I think one of the ways that used to happen was, so for example, you have a list of servers, you get your, you have a key, you kind of hash the key, and you kind of do like, for example, you can do like a simple modulo on the number of servers and route the request to those servers. And data gets stored, etc., on these servers. So this is how you partition, or this is one way to partition. The issue with this kind of process is that whenever you add new servers or remove servers, then the keys that you've added in the past may no longer be like the servers that they were routed to previously may no longer be the servers they're routed to today, right? So when you hash them and do like a modulo on like a different number of servers, they might land in a different server, right? Um, and the downside of that, for example, was that um, you need to like recalculate a lot for like every time you add a server, you need to like recalculate almost all the keys so that they're placed in the right servers now. So Dynamo anyway uses constant hashing, which is kind of an improvement on that. Essentially, you think about the hash space as sort of a ring, and the concept of it being a ring is just like I don't know, the maximum value in the hash space is routed into the smallest value in the hash space, so it kind of forms a ring. And so think of a ring and think of like the ring representing the hash space and all the values that the hash can give. And both requests and servers are, or keys and servers are hashed onto that ring. So a server will be hashed and placed on the ring, and then a key or a request will be hashed and also put on the ring. And the way like requests are processed, so a key would look for the first, or the request will look for the first server on the ring when it goes clockwise, and that server is the one that handles the request. So that is what consent hashing is. But and so the way the servers are placed, like every server that comes is kind of given like a place randomly on this ring. So it's placed in a random position. And you can kind of think about like this posing some sort of issue where depending on the position of the rings, or sorry, the position of the servers on the rings, it's possible that some servers will handle more requests than others, right? So it creates something called hotspots.
Mm.
And so it's possible for servers to like handle more requests than other servers, and for some more servers to be overloaded. But also like another issue was like this method didn't really take into account the fact that different servers um, could have like different capacities. So for example, some servers have they could have more RAM or more CPU and so can handle more requests than others. And yeah, this like initial approach also did not account for that. So what eventually ended like what like Dynamo eventually did was to so for each server, instead of placing it in just one location, you place it in multiple locations. And these multiple locations are called virtual nodes, or tokens, right? So you kind of so in initial approach, you give the server one token, so it's in only one spot on the ring. But in
Mm-hmm.
this new approach, you give like a server multiple tokens, and it is placed in multiple spots on the ring.
Mm-hmm.
And in this way, the hotspot issue that we had before is at least alleviated. Like it's a lot better than before because now servers are placed in multiple locations and like requests are being handled in a more distributed way. And this new approach also um, is great for like heterogeneity because which is like servers having their own like different servers being able to have their own spec and capacity is great for this because if a server has more capacity, then it can just have more virtual nodes, right? And it can handle more requests. And so this was eventually like what the paper discussed. In like a later section, they did discuss like improvements upon this partitioning technique, but I guess if we get there, we can talk about them. But yeah, this was I guess in short, what their partitioning strategy was like. Yeah.
Okay. So, like on the idea of virtual nodes, so you had like physical nodes then, like that were actual nodes, and then the virtual nodes were just like the different positions on the ring that they
Yeah. So
like.
the virtual nodes are is how do I how do we think about this? Just it's an abstraction,
Mm-hmm.
right? When you remove the layer of the virtual node, it's a new node. So think of virtual node, for example, if you think of virtual node as a class, for example, virtual node would be one property would be the actual node, so the
Mm-hmm.
actual node's ID or something, and another property would be the token, right? So the actual node points into another token. Or you can think of it like the actual node, the key of the actual node in a map, and then a list of tokens, and each token represents a virtual node, like so. Yeah. So the
Yeah.
virtual node is kind of like if you remove the layers, it's the real node.
Mm-hmm. Right.
Mhm.
Okay, that's interesting. And do you think this was something that I guess existed before Dynamo, or was it an innovation that the
No, no, it existed before Dynamo because in the paper they referenced another paper where they talk about
right?
this. I don't know though if like this had been implemented before. Like this is not something that I checked. So it's possible that in the usually like if they're going to introduce something, they would have implemented it in some shape or form. But I
Mm-hmm.
don't know if whatever implementation was done before was to this level of sophistication or like scalability or
Scale, yeah.
yeah. So sorry, scale, not scalability. So so maybe that's what the innovation was here as well.
Yeah, yeah. I think I kind of read that the what was innovative about it was being able to make it work on such a large scale. So
Yeah,
yeah,
and that is the like the devil is in those details because I mean the theory of the systems are very usually very interesting and very and then when you start implementing you like notice like these very little things and it kind of leads me to another conversation about so Amazon cares I mean they cared in the paper and I think they still care today about how like every customer is experiencing their products, right? So they have this concept of, I think at the time, I think today this is not the case, but at the time it seemed like um, systems used to measure like their metrics based on averages and medians
hmm
and stuff. And the problem with that, for example, saying like there's like the system is available 99% of the time for, I don't know, the average number of customers. The problem with that is that some customers, especially the big ones with like a lot of workload that are kind of outliers, would may experience like very poor performance from the system, but that would not
hmm
be tracked.
hmm
And at least from the language of the paper, it seemed like this was this was like a new thing to do. I think today is very common to track like P90s and P99s and P99.9s, but at the time I don't think it was so.
hmm
At least that's the language of the paper from my point of view. And so it seemed like at the time they cared about like 99.9, like what is the 99.9 percentile of all of our customers experiencing? And
Right.
when you start thinking about like the fact that you want the 99.9 percentile of all your customers to experience the same level of performance then you would need to think very creatively. So it's now not just about, I think my point, the point I'm trying to make here is not just about even implementing those things on a production system and getting them to work. It's also getting them to work for the 99.9 percentile of like all of the customers that uh Amazon has, right? So
Yeah.
yeah.
So what does like partitioning achieve? Is it in terms of scalability, so being able to like incrementally scale the system by just adding nodes? And does it also like help with performance? Yes, right.
So there is a formal definition of scalability I'm trying to remember, but think of it like I'm going to butcher this definition because I don't remember the way it was said. But think about it like this, that for like if you double the number of servers on your system, your level of performance should also double.
Mm-hmm.
Um, and like that's what being scalable means. So I don't know if like it's being double is exact. So if, for example, if you triple the amount of servers, like your performance should triple, for example. Like let's just go with that. So if we say like scalability is like it's not just about adding servers. Like if I add servers, does my performance improve in kind with the scale I'm adding, like with the number of like resources or servers I'm adding? Like that's the only time where like scalability becomes is important. Like adding servers without getting like an in-kind performance from that is just a waste of money.
Mm-hmm.
Now, if like you think about um one of the issues that the like one of the reasons why they had to build this was because I think traditional systems didn't have very good, at least at the time, today it might be different, like partitioning techniques. And so actually before that, so think about a scenario where you store all of your data on one server. Like it's possible to store like I don't know, like you on one server, for example, you can have like petabytes of data today. You can have like I don't know, a lot of data. But so storage is not the bottleneck. The bottleneck is usually like compute. Like it's usually like what the CPU can do and so
Mm-hmm.
on. So if you store like all the data on one server and you make like millions of requests to the server, a lot of those requests will be stuck, right? And you wouldn't like get the response and performance like response time and performance you want. And so one of the main benefits of um, scalability should be that if I partition, so partition gives you scalability and scalability should give you performance. So if
Mm-hmm.
I partition my data in multiple servers, I can split the amount of requests that are being made to each server, which should give me higher performance because now I have like servers handling these requests in parallel, right? They're
Mm-hmm.
handling it with their own CPU, with their own RAM, with their own resources, and I should be able to they should be able to um serve this request in parallel, right? So they're not blocking
Yeah.
one another. And so the point of partitioning is that I can isolate like segments or sections of my data and store them. And because I'm storing them in different places, requests can be made to those specific sections when they're needed. And like this should give me better performance. Something that the paper mentions is that um, your level of scalability and so there's something else I don't remember, but level of scalability is like bottlenecked by how you manage your application states, right?
Right.
So if you store your you store your state poorly, or you store your state in only one place, or even if you partition, you don't partition correctly, like all of these come to represent like the application state. If you don't do this well, you find, for example, you have single points of failures, which will affect performance. You have like systems where you're bottlenecked by like the capacity of like maybe one server if you're storing on everything on one server. Um, and there are other issues that come up. So go to the original question. Benefit of partitioning should be that you get like you get increased scalability, we should also give you increased performance.
Mhm.
But this is also kind of dependent on what your partitions look like. If you like like we talked about that Dynamo did, they had to introduce the concept of virtual nodes so that certain servers were not getting hotspotted.
Overloaded. Mhm.
Exactly. So yes, so partitioning should give you performance, but there's a question mark. You need to do that correctly, basically.
Yeah.
Okay, yeah.
All right. Okay, so another interesting concept was how they handled replication. So I think first we want to talk about why it was even like important to have replication in place and
Mhm.
how they did it.
Why is replication important? Again, like we're going back to the like states like what we said about states limiting your level of performance. Like the way you store application states will determine how much scalability, how much performance you can get.
Hmm.
Now, assuming that there's no replication, means data is stored in only one place. We go back to the same issue. If data is only stored in one place on one server, you get a single point of failure. If that server becomes unavailable, like certain requests will not be cannot be performed, right? Cannot be fulfilled, which will I don't know. Like there's a lot of things that come out of that. Like you break customer trust, you lose if you lose customer data, that's like a big issue, etc. etc.
Hmm.
So replication is just a way, like one of the like a strategy to make sure that you don't have single points of failure, but also kind of fits into um the idea of hmm. Okay, I don't want to confuse myself. I'm going to walk back and talk about. I want to talk about this in the context of partitioning, but there's something
Hmm.
that's unclear in my mind right now, so I'm going to visit this later. Anyway, when the so the reason you replicate is to like make sure that data is stored in multiple places, and if like some, for example, like a server is I don't know destroyed, like data centers, you can think about data centers being destroyed, for example, like you can think about this blowing up.
Hmm.
Um, you can also think about scenarios where, for example, some servers just become like maybe because of like network partition, some servers become unavailable. If like data is not replicated in all of these scenarios, then it's possible that customer data is lost and requests can be fulfilled, right? So that is like benefit of replication in one
Hmm.
of them, in short. Why, how did like Amazon do this for Dynamo? So remember our ring that we use for partitions.
Hmm.
Um, remember where we are now is that nodes are placed in different sections on this ring,
Hmm.
and those different sections are called retro nodes. So you think about like having multiple nodes with multiple positions. Now, it's possible like I go into a ring, for example, and I see 30 nodes, quote unquote. But it's possible that there are actually maybe six distinct nodes, right? And each like of the six have like five retro nodes like on the ring.
Yeah.
So what Amazon would do is to replicate would be that the data is stored on. So for example, I think you give these values in, so they have like configurable variables where they allow you choose how much replication you want.
Hmm.
So let's say you choose three and you want to store your data on like three nodes. You will, data will be written to like the first node. The first node will now replicate the data into two other nodes. Now remember, it's really important that the data is stored on the like distinct nodes, or I don't know whether to call them distinct or real nodes. So remember we have
Yeah.
virtual nodes and we have, let's call them real. So we have virtual and we have real nodes, or so it's important that the data is stored on three real nodes, not virtual nodes. Because if you just store on virtual nodes, it's possibly just storing in
Of the
three versions of
same
the same node.
of
Exactly.
the same
So
media.
um, you store in three distinct real nodes, and like yeah, like data eventually gets to those nodes. The concept of like eventual consistency is that if a request is made and eventually gets to, for example, those nodes, like before data gets to them, is like they would return um like they might return like stale data. So it's really important that Amazon like built, so the system is being built for like a specific set of requirements,
Mhm.
and this requirement should allow for this eventual consistency, right? So yeah.
Okay. So it's like I think what helps me understand like partitioning and like the ring space
Hmm.
is that each node, let's say virtual or not, is responsible for a space in the ring. And any key that falls within that space, that means any data whose key maps to a position on that space that that node kind of like is in charge of would be stored on that node, right?
Hmm.
So different keys map to different nodes. So different keys will be stored on different nodes. And that's kind of like how what partitions the data, right?
Hmm.
And so now when that key is stored, that node has its replicas that it must always replicate to. And so it's like there's a circle, there's a node, and the node, let's say you set n, which is like the replica number, to 3. The node
Hmm.
has to replicate whatever data is on it to the 3 next nodes on the
Two,
ring. Sorry, to the
because
2,
it's a bit, yeah.
yeah, so the 2 next nodes on it.
Yeah.
So yeah, so that way like data is stored on different, like data is stored on different nodes, but each node makes sure that whatever data it owns is replicated to other nodes as well. So that if it
Yeah.
like dies, data is still in other places. So I think that's like, yeah, how like replication and partitioning work hand in hand to like,
Yeah.
yeah, that makes sense. So the next concept we could talk about is kind of like how, so we could talk more about like the variables that Dynamo gives you. So I think like a major thing for Dynamo was to give its clients applications or its use cases the ability to configure read, write, and replica numbers really easily so that they
Hmm.
could achieve whatever level of availability, consistency, and durability they needed. So we could talk more about how those read, write, and replica variables change and how they could influence how the system works. In the paper, they talked about this more in like under quorums and how quorums work.
Okay. I want to open the paper. Give me a second. Do you have a section for me?
Yeah. Um, okay. So there's a place where they talk about it more interestingly. 4.5. Um,
4.5. All right.
yeah. And
Okay.
then yeah, I think we'll start with that.
Okay. So what's the question again? Ask me again.
So how can we configure read write and number of replica variables
Yeah.
to
Okay.
achieve what we want?
So they're like there are three variables that the paper talks about, N, R, and W. N is number of nodes I think you want to replicate to. I think this is what N is. So eventually all of these like three nodes, for example, if N is three, eventually three nodes should have all of my data, right? At least three nodes should have all of my data. R is for reads. So if I say R to two, for example, what this is saying is for reads, I want to have read from two nodes that have my data before I return a response to the client. And for writes, if W is 2 as well, I want to have written to two nodes before um, I like return like a response as well. So you can essentially kind of configure, you can kind of see how you can play around with these numbers to kind of get more availability slash more consistency, for example. So for example, if your R is W, as long as you find one node where you can read from, you're not kind of bottlenecked by the latency of
Your R
another
is
node.
1.
Yeah, if your R is
Okay.
one
Hmm.
and you want to like, so you want to read something, you kind of load the page, you want to read something, you're not kind of bottlenecked by the latency of like reading from another node because essentially here, if you want to read an R is 2, now your performance is kind of constrained by the performance of these two nodes.
Mhm.
and both of these nodes needs to be within whatever performance you want, and it needs to give you the data in that time. So if R is one, you get like more. There's like you get more from that. Like your system is probably more available. If there's like a network partition, as long as you can access like one server, you return a response, right?
Mhm.
But I mean, the downsides of that, like one of the things that the paper also talks about is like object versioning and how you can handle like conflicts and stuff if your nodes are they're conflicting. Um, like some of the objects that have conflicting versions between multiple nodes, right? And if you're only reading from one node, you're not going to get any conflicts because that one node is going to have um like it's going to know about
What data it has. Hmm.
its own version. So I guess it's faster. Like you don't have to think about merging, you don't have to think about like addressing the conflict. But the issue is that if there is like a conflict that is should be addressed, like because it is useful to, you kind of miss out on that one. Two, um, you also like if there's like a more recent version. So sometimes there's like a merge that you need to take both objects and kind of combine them into one new thing. Like so you take some parts of both. Sometimes they're just like newer data. So we go back to the point about our eventual consistency thing. So if you don't care about like the consistency of your application and you just want to read whatever version is available from whatever node, then yeah, I guess R1 works. And same for like W1, right? So you want to write your data to just one node and you go. So this will make writes very quick because you just need to write to one server and that's fine, right?
I think it's like you still write to n servers, but you only wait for one to like confirm
Yes, you
a
wait for one
successful
to
write.
exactly. Yes. So for if n is three and w is one, you only wait for one to confirm to you before you move on. Now it's very
Yeah.
important that one. I I don't know if I might have missed this detail in the paper, but it's very important for that one node to write to disk so
Mm-hmm.
that if the data like if the server like crashes or whatever, the data is still preserved and it can eventually get to the other nodes it needs to replicate. Because if W is one and data is stored, for example, in RAM, and the server crashes, like the customer's data is gone. And this is after like a confirmation has been given to the customer. So
Yeah.
um, I'm pretty sure that they needed to write, if W is one, you need to write to disk so that
Mm-hmm.
like data is preserved. So the customer needs to wait for the whatever time it takes to write to disk in that one server. And I think as long as it's written to one disk in one server, it eventually gets to the others. So you can kind of, if you want more assurances that your data is replicated, for example, across, I don't know, different nodes, across different regions, whatever, and you can have like higher numbers for writes, for example. So W could be like two or three or something, and that way, until the data is written to multiple nodes, you don't get a response. So like by the time you're getting
Yeah.
a response, you're sure it's written to like multiple places.
Mm-hmm.
And I think like one, maybe one, like one, be I'm not sure. I'm not sure if this was like me like reading commentary about the paper or like reading this in the paper, but there's also like optimizations that you can kind of like do here. So where like you have, and I don't know if like this is configurable on some other system settings, but something that I read somewhere, or either was in paper or commentary, was that you can also, because the problem is, for example, if you have like a higher number for W, so let's say you have three,
Mm-hmm.
typically what that means is you need to write to the disk of three servers, right? You need to wait for the writes to be written three disks before like the response is returned. But I think like there's a way that you can write to one disk and write to the RAM of the two other nodes, for example. And those nodes will be much faster than writing to this. So you get response quicker from those nodes. And in it's only written to like one disk. And so it's written to one disk because you have to make sure the data is never lost.
All right.
And it's written to the RAM for the others so that if assuming everything goes well, like it will go from their buffers, from their RAM to their disks at some point,
Eventually. Mhm.
but you get like your response time faster. So I think there was an optimization for that. Somewhere, I'm not sure, again, I'm not sure if it
Is
was
it
the
where
paper
they
or
talked about like durable rights?
I think
And
so.
yeah, I do remember that. So that was kind of like how they they traded off durability in some way for performance.
Yeah, exactly.
So yeah, because the whole point of durability is that you are sure that the data is stored inside the
Yeah, it
storage
can't
of
lose
the
my
node.
data. Yeah, so exactly.
Exactly.
So
But then like they took it a step further and were like, okay, so the data can be stored on the storage of one node, and then like for the other nodes just store it in like a cache, like object buffer kind of thing. Kind of
yeah,
reminds me of a cache, the way object buffers work. So
it
yeah,
is.
which is really interesting. And then there's like a thread in the background that eventually like moves it, to
Yeah,
the main storage of the node. But it's like, yeah, like this was what I was saying, like how like they just push the boundaries of everything a little bit further.
yeah.
But yeah, I think so.
And I,
But the fact
and
that there's like,
I
yeah, I
think
was,
that to talk about the sorry
mhm,
to interrupt. To talk about the SLAs that we talked about before, I think one of the reasons why they introduced this optimization was because they realized that some of the like performance that some of the 99.9 percentile of their like customers were getting was low. And I
mm,
think this optimization like reduced the issues they were seeing by like 5 factors, right? So
yeah,
it
I
like made
remember.
the performance better by like 5 times better than what it was. So
Even in
I
the 99 percentile.
for the 99 percentile specifically, I think. Um, I might be wrong about the actual figure here. Like maybe it's not 5, but at least by a number. I don't remember if it was 5 or more, but it did improve it by a lot.
Hmm.
Yeah.
Yeah, that is pretty cool. And like, I guess the whole point of quorums in the first place, like why you should have like a certain number of reads, like why you should ensure that a certain number of reads have happened or a certain number of writes has happened to consider a request successful is because like you have multiple nodes, so there's going to be like a chance where there's different versions of the data across the
Mhm.
multiple nodes, and you want to kind of like get so basically a quorum is that more than two people or two or more people agree on something. So you want to
Mhm.
make sure that okay, two nodes agree that this write has been done and this write is successful before I send it to,
Mhm.
the client and all. So I
Yeah.
think that's good. They mentioned that like an optimal configuration for N, R, and W is that N is 3.
Mhm.
So you're making sure that you are writing to 3 nodes, 3 replicas, and then
Mhm.
R is 2. So you are making sure that, okay, so let me start with W being 2. W is also 2. So you're making sure that of the 3 replicas you've written to, 2 can confirm like a successful write has happened. And then R2 should also be 2, so that if you are, so I guess in this case you're reading, right? So if the client sends a read request, you want to get your response from 2 nodes. You want 2 nodes to agree that okay, this is the response that we are having, and so this is fine to send. So yeah, that
I
was
don't
just
think
like
I don't think that it needs to agree. I think that they just need to. So I think this leads us to another important part, I think, of the paper, which is versioning.
hmm.
So it's possible for your data to have multiple versions, right? Like eventually, like, and you
All
can think
right.
about this being possible with like stuff like network partitions or like some issue happening, and so or concurrent, like so network partitions plus concurrent writes can eventually like make it so that different servers see different versions of some previous version of data. Now, the paper talks about how they make it possible to address this conflict. So when you have different versions of data, like that's a conflict. You need to address this conflict at some point, somehow. And so the paper talks about two different ways to handle the conflict. One is the system itself, so Dynamo. addressing the conflict, and it's called something like syntactic
Syntactic reconciliation.
reconciliation. And this is where they're able to figure out that, okay, for sure, this version is should supersede this other one, and we're sure that this these other version can be done away with. But there are times when you can't tell, right? And like this also comes into the importance of the reads, for example. So the time where you can't tell and Dynamo cannot resolve it, because if you force Dynamo to resolve it, Dynamo only has like simple policies like, okay, they'll just pick like, okay, which one was the latest one, and it
Yeah.
just like
Last
chooses the
right
latest one.
wins.
But sometimes you don't want that, right? So they make it possible for applications to handle these conflicts themselves. So they expose interfaces so that you can handle this thing yourself.
Hmm.
And the way they do that is when you, for example, read, this is important. When you read and R, for example, is 2, and two nodes are seeing two different versions of data,
Hmm.
the read will return this two. If the node have two versions of data, the read will return the two versions
Right.
if Dynamo cannot resolve it. And you have to, you being the client or the application, would have to like resolve this yourself. And this is good because you understand like the schema, like what the object is meant to be. So this is
Hmm.
called semantics. So you understand the semantics of this data. You understand what it means to you, what's like should replace another, blah blah blah. So they give you the opportunity to do this. And like you tell them, okay, between these two versions, what do you want to keep? Or like what's the combination you want to keep, etc. And like you can write back with um the version you want or the new version you want and what the data you want to keep is, and it kind of
Hmm.
supersedes that. So if you're only reading from one node, you're never going to get the opportunity to do that because your node is only going to see one version, right?
Hmm.
And I think one like when I think about, I don't know that people talks about this, but I think about like if you're reading one node, it's probably best you just like let Dynamo pick last right wins so that all the versions can be handled, like all the conflicts can be handled like a very simple way. Because I don't
Yeah.
think reading from one node will give you the like multiple versions that you need to have. Like if you only need to read from one node,
Hmm.
I don't think that will give you like let you know that there are multiple versions you need to reconcile. Yeah.
So, okay, so that makes sense. So it's not like the nodes are agreeing that they are seeing the same data before they send like a response. They're just sending what they have. Like
What they have
it,
about the data, exactly.
right.
Yeah.
So if we were to, I guess, paint this picture better with the shopping cart situation on Amazon. So let's say that the way regular updates work is that first I add one item to cart. That
Hmm.
sends a write request to the node.
Hmm.
Then I add another object to the cart. So that sends
Hmm.
another write request to the node, right?
Hmm.
And we have our first request with just one item. And we have our second request with one item, but it's like it knows that this is so in that situation, it's like there are two versions of the cards with one item each, is the way I'm seeing it. But in order to reconcile this data, like you can see that one request happened before the other. So
Hmm.
the last request will be the most up to date version of the card. Or actually, let me change that. I think you end up having the first request has one item, and then the second request that you've added one more item to, it sends like what is currently in the cart at the time. So then the second request has two items, right? Not one more.
Um, yeah. So I think that maybe maybe like a good example can think. So think of, and I think this happens to me a lot. So I for some reason, I sometimes open my Amazon on multiple tabs.
Mhm.
And some of them I like go between the tabs to like add. Actually, like this is actually very possible because sometimes I want to see a product and I open a new tab for the product,
Mhm.
and I do this for like a lot of products. And I'm kind of going through each tab. I'm like, okay, do I like this product? And I add to cart, I add to cart, I add to cart in this different one. And you can kind of think about like how like those different tabs pointing to like whatever they're writing to like different servers, like different servers. Um, and maybe like when you add in the first cart, the in the first tab, you add to like server A. But by the time you get to second cart, server A is unavailable, so you write to server B. Now let's assume that there are three servers in this situation. All of them have like maybe some version of the cart. Maybe like you want to add, I don't know, 50 items, and they all have the same version by the time you've added 10 items, something like this. And so you have your first tab open, you add something to cart, it goes to server A, like server A knows about it. But at that point, server A, once he like server A gets the rights, he kind of gets partitioned away. It's like, okay. And you go to server B, you write to server B. Server B cannot see what you've written to server A because it's partitioned now.
Mm-hmm.
So you write to server B. Server B writes to like so server B has the initial version of the cart. It knows the initial version of the cart. It creates a new version of this cart with the new data you've added. And so let's say, for example, the initial version of the cart was version one. Maybe this is a good way to think about it. So version one, all of them have version one because version one has two items. So version one with two items. The first tab you write server A. Server A sees that, oh, the initial version was version one, now is version two. I'm the one that wrote to it, so I'm saving the object version now as two with all of the updates I've made to it.
Mm-hmm.
But server A gets
Disconnected
partition.
somehow from
Yeah,
other servers.
I go to server B. Server B cannot see that server A is not cannot be contacted, so it hasn't like data hasn't gotten server B. So I write to server B now, and server B only the version that server B knows about is the initial version as well. So server B like writes this um its own like data with creates the new version. So the version will now be version 2, and server B has made the change. So now you have server A with version 2 and server B with version 2 for the same object. So and now, like at some point, like server A comes back online, and now you have server A and server B both with version 2 or something like of the same
Like
object,
two different, yeah.
and and um, they need to be reconciled.
Mm-hmm.
So one possible way of reconciling this is to say maybe like by with like time like epoch seconds. Which one was the one that was written last, and choose that one and discard the old one. That is one way. But we probably don't want to do that, right? Because it's like if you do that, let's say server B was the latest one. So you like kind of discard everything you wrote in server A. So imagine like in server A you added like I don't know 59 items to cart. And in server B, in the second tab, you added maybe just like four or five. And so by the time you're reconciling, if you just choose latest epoch, all your 59 items, they're gone. It's like,
Mm-hmm.
so it's probably like not like you don't want to just you might not want to apply the simplest like merging
Reconciliation
strategy.
technique. Mm-hmm.
And this is like one scenario where, for example, if you read from so server A comes back online, server B is also online, you make R equal to 2, and your client is trying to read, it reads from server A and server B when it's reading like the card again,
Mm-hmm.
and it sees that there are two different versions of this thing, and okay, what do we do with these two versions? And it chooses to combine them because the application understands that, oh, okay, these are two like cards with ads, and I want to keep them.
Mm-hmm.
So like in that way, like you kind of see how one being able to get the different versions from the servers allows you to reconcile yourself and you kind of decide what is best for you.
Mm-hmm.
And because if we choose like the default policy, we like it might not be the best for like an add to cart situation. Um, I actually forget what your initial question is that got us here, but like
I was,
this is sorry, yeah, go.
yeah. No, I was just like wanting us to use an analogy, like an
Okay, yeah.
example.
So yeah,
Like,
this exactly. Okay, yeah, I remember that. I remember that. So this is like how I would think about, for example, what a reconciliation process could look like, and how like Dynamo giving like a customer's ability to reconcile, like implement their own reconciliation is like a very good idea.
mm-hmm. Right. Okay. That makes sense. So that's how Dynamo handles like data versioning and reconciliation.
Yeah. There are times when it can decide for itself that all like a version can definitely supersede others. Like if all the versions that a server has is newer than all the versions that another server has. For
Hmm.
like it can decide, okay, yeah, this is definitely newer than this old version, and we can discard it. So
Yeah,
sometimes it can decide for itself, um, but sometimes it can't. So
yeah. I guess it's easy for it to decide for itself when it knows that this version contains all the other versions plus like an update. So then it knows that this is the latest.
yeah, which is what the version numbers give. If, for example, all my versions are two for the all the like for an object, my version is two. Um, and the server A only has version one of this object.
Hmm.
This server has probably seen version one or has seen version one as well, and the
Hmm.
version is now two. So it's kind of it already knows about version one, and it doesn't need to do any reconciliation. It can just discard that.
All right. Okay, so this is what happens like during reads and writes, and how like the system knows what data to return during a read or yeah. I wanted us to talk about how it handles like so you see the replicas, they are always meant to have like they're always meant to be in sync. They're always meant to have the same like I guess version of the data at a time,
Hmm.
right?
Yeah.
So what happens when like we said now two like nodes have different versions. Fine, when a write happens or when a read request happens, they send both versions of that data to like the client. But how
Hmm.
do those nodes now, after like replying the client, how do they now like sync? How do they handle their differences?
So the paper talks about an anti-entropy mechanism. So
Protocol.
entropy is I think entropy means disorder, something like this. And anti-entropy is essentially trying to reduce the disorder in the system, right? So in this case, we can think about it like reducing the amount of or the skew like every replica should have with each other, right? Like they should have the same version of data ideally, and we want to kind of as much as possible kind of reduce the the skew between like nodes that should have the same version of data. So the way that they deal with this is with something called Merkle trees, which I hadn't heard about until this paper.
Yes.
And I think that the way Merkle trees work is it's kind of a tree of hashes where at the base you kind of store hashes of keys and you kind of hash children to form parents and hash and do keep doing that until you get to the root. And between like two different nodes, you can kind of compare the Merkle trees to find out if they are in sync. And you can compare ranges to see. So if the roots are not in sync, you can keep like searching through the trees to find out which ranges are not in sync and if they should be in sync. And if they're not in sync, then a node knows exactly what range of keys it needs to fetch from another node. So I think that's how it works. I haven't implemented this myself. Don't know too much of it in detail, but like on a high level, like that's what I understood. So microtrees present this idea of comparing ranges to improve anti-entropy because it's kind of easier to compare hashes than to try to compare like individual keys stored across multiple nodes. But if you compare the hashes instead, it's easier to search through those. And you can quickly discard ranges that are in sync because the hashes match. You can discard them and focus on the hashes that don't match and like keep searching for what range in this hash or in this place does not match. And yeah, you can copy those exactly.
Mhm.
Yeah.
Okay. Okay. So I guess we could also talk about how like nodes are added and removed from the ring. Like what happens when they're added and what happens when they're removed. So
Um, sure. But like, I mean, do you want to try that? Like what's,
mhm.
yeah.
Okay, so I guess that's like Dynamo's membership slash failure detection. So how does it know when a new member is added? And how does it know when, or rather, what happens when a new member is added? And how does it know when a member has failed?
Yeah.
So the way I understand it is when a node is added to the ring space, it kind of has to like recalculate the distribution of the keys amongst the nodes. So yeah, like the node now is like they can it kind of reshuffles the keys so that the new node can also like be in charge of some keys within this space. But I think there's also like something interesting they do in that regard, but I can let you talk more about that. But as for
Yeah.
like yeah, I think for I can talk about like failure detection as well. As for failure detection,
Mm,
the way it works is that it works by this gossip protocol. So when a node fails, like the node that I think so each node like does like a random check on different nodes at different points in time.
mhm.
So when it realizes that a node has failed, then it tells like the other nodes. So that's like how nodes know that
Yeah,
okay,
but what do
that's
people call that?
what does what?
This the paper call that like this thing where nodes are kind of sending data to like information to each other. It's kind of a gossip. It's like it calls it like a gossip protocol where
Yeah, it
basically
said that.
oh okay okay I missed that. So it's basically like where yeah so the servers will like a node will try to contact another node and it realizes that it can't talk to the node so it records it
Hmm.
itself and eventually it's sending like data to or its state to multiple nodes so that multiple nodes eventually will get this this state. And if there's a newer version, so again, like come to version is kind of important here, I think. Like they need to also have conflict resolution for this, I think. Because if another node has accessed, if for example server A tried to access server C and server C was not available, and server A is trying to tell everybody that server C is not available, or like nobody should talk to server C. Oh. But server B accesses server C and is like, and it's newer, and it's like, oh, server C is actually available. They need like a way to know what version is newer and how to overwrite that. So they also probably have like some conflict resolution thing. They probably use consensus algorithms for that. I think that's kind of like something that consensus works really well for. Um, eh, consensus is essentially like a merge conflicts. It's like a conflict resolution mechanism, to be honest. It's like how does everybody agree on what the current state should be?
Hmm.
But that's kind of a different direction. So yeah. Um, for adding and removing nodes, I'm trying to remember what section this was in. Duh, duh, duh. I have the paper open. Let me see.
Yeah,
4.9.
4 point, yeah, 4.8 to 4.9, I think.
I see. Yeah, I think like it's a combination of what we talked about. So it looks like when a node is added, it needs to be like for the so it's possible like for example a node is like a server is added for the first time ever, right? And it needs to be registered on the system. So I think they have a store where they register like a server that has joined.
Hmm.
And it looks like they do this like addition manually. But it also looks like a server can leave and come back. So a server that has been registered before can like leave and come back. And I think that one, it now just forms like a history from that initial addition. And the way that a server gets bootstrapped is when you get like placed on the ring, it gets assigned a couple of tokens. You now know the range of tokens that this server should handle. Now remember, um, anyway, it knows the range of tokens that this server should handle. So it takes the set of tokens from the next node. So what I was saying now remember that there is like replication in process here, where if I want to store a key or a range of keys in like n nodes, I save it in the first node and n minus one nodes after. So if I move the key, like a range of keys to a node, I kind of need to move all the replication by one step. Like I need to Actually, I think I could just go to the last one and take it and bring it to. Actually,
because
yeah.
it's a ring.
Right. So I think that what can actually happen. So this should actually be easy. So I don't need to move the nodes in between. I think you just need to go to the last one and delete it. Once the node is added to the first one, then all the data for that range in the last node. So I add a new node. I'm storing stuff in end nodes. I add a new node. The new node is now at the beginning, let's
Hmm.
say. And now just go to I move the key to the new node and I now remove the last node. So that way I only have to talk to two nodes, not just so it's possible that n is 10, for example, right? And in this case I just need to talk to two, which is like the one I'm adding and the last one on the list. Like the last node that was replicated to. Does that make sense or is that confusing?
Like I'm trying to figure out why you're adding and removing at the same time.
I mean, you add first before you remove. But the point why we're doing that is, so remember, we're replicating the keys. We replicate the keys. So we have, for example, let's say n is 5. We need to replicate the keys to 5 nodes.
Hmm.
If we add a new node so we're replicating, let's say, range 4 to 5, 4 to 10 keys, 4 to 10 are being replicated 5 times.
Hmm.
I now add a new node that can handle 4 to 10. This new node should get all the data for 4 to 10 into itself.
Hmm.
But now if I just add 4 to 10 into itself, now 4 to 10 is replicated in 6 places,
6.
not 5. So instead of moving one by one, like moving in the ring, going one by one and moving the data to the node before, I just need to go to the last node and delete what the last node has, I think is. So that would be like a more
Yeah.
efficient way.
Delete the last node store of keys
4 to
4 to
10.
10 because the last node might have like
Oh yeah,
would
not delete the
would
node.
have.
I'm
Yeah.
I'm yeah, 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 just 4 to 10. Yeah, not the whole thing.
Okay. Okay.
Yeah,
Yeah.
yeah.
Yeah. Okay. Okay. So should we like put things together and talk about like the life cycle of a read, the life cycle of a write, and how all these things like come into play?
Yeah, like yes, I think we can try that. Do you want to try and start,
Mm,
or do you want me to go?
I can try for like a read in a an optimal scenario where no failures happen first. Um,
Hmm.
okay, so we have a client and then we have like Dynamo.
Uh-huh.
And so let's say the client is like Amazon.com, the e-commerce platform. So Amazon.com sends a read request to Dynamo to read data from Dynamo. So by the way, it's doing this by sending um I guess it's sending like the key whose data it wants to read.
Hmm.
So this request gets sent to a node. I feel like it's any node in the ring space. And
No, not any node. Remember, okay, I don't think we talked about this, but nodes have a preference list. I actually don't know how
no,
the.
but like I feel like it's before it gets to the so the any node now has like a preference list of
Okay, nodes
nodes for
preference
that
list.
key.
I see.
Yeah.
Okay.
Yeah, that's what I think. So yeah. By the way, there's a load balancer in between this normally, like sending, so it doesn't go to a node that is already like overloaded with previous like requests, other requests. So the request gets load balanced to a node that can, do execute the request at the time. So
Uh-huh.
that node in like if it wasn't an optimized system, that node now has to start like searching through all the other nodes in the system to know which node is responsible for storing this key. But the
Uh-huh.
way Dynamo does this is that each node, because like the keys are mapped by consistent hashing to a position on the ring, each node can mathematically calculates where this key is on the ring. So it just needs to hash the key and it gets like a position on this ring. Oh, this key is in like this position of the ring. And
Yeah.
because it knows the position of the key and it knows the location of every other node in the ring, so it stores like a table of like each node, each other
Mm.
node and their position on the ring. because of this, it knows the node responsible for that key, right?
Hmm.
So now it knows the node responsible for that key. So it just like sends the request straight to that key, one go, right? And so now we are at the key in charge of this node, and I'm guessing that is now what becomes we're the node in charge of this key. I'm guessing that's now like it becomes the coordinator node. So now, you don't think so?
So I so there's something I'm kind of unsure about right now, where I don't know if, for example, when we're reading, if the node needs to get to. So we know that the node that I need to send it, when I think about the partitions, and I think this helps me with the coordinator thing. When I think about the partitions, I think that partition should just be where the data is stored, not what to process the request. So if we kind of separate the request processing from the storage of the data, which is now the partitions, maybe it's easier to think about. I'm not sure, but I'm trying to figure this out right now. So if like we say that we read, I think what happens is whatever so you mentioned there's a load balancer. Load balancer sends this request to any node that's kind of free on the ring, let's assume. Now this ring it knows the nodes that should provide a response for this request.
Mm-hmm.
I don't know if at least I'm assuming that instead of forwarding the request to the node that should handle this request, it just makes the request to this node. So it knows like the nodes that should be handling the that should have this data in their storage,
Mm-hmm.
and I think it should make requests to those nodes. And the first one or the first R that return responses will send it to this node, and that node will send the response back. So I think
So
some yeah,
are you
okay.
saying like the difference is in that it is not forwarding the request to the node, but it's making the
Yeah, like
request to the
I'm
node?
wondering if that's what it means, because I'm wondering if like because I'm trying to think of what the benefit of the load balancer is. If like there is only a set of nodes that can handle the requests. Is the load balancer, yeah, go.
Like the load balancer doesn't know where the partition is. It doesn't know where that key like is partitioned to. It's blind to that. So it would send it to any node in the ring.
Right. But right. So it's like, remember that there are two ways that we can kind of coordinate this, right? There is the client, where the client already knows ahead of time what the preference list of these keys are. And the client just directly calls those nodes. So um, it can call like node A, node B, node C, if like node A, node B, and C are the ones that contain key X or something, right?
I don't know that the client is partition aware. Like I don't know that the client knows.
So if we go to, let's give me a sec. If we go to, I think the section is 6.4. Give me a second. I need to remember what was said here.
Okay, it's 4.5, the second column, that there are two strategies a client can use to select a node. It can route its request through a generic load balancer that would select a node based on load information, or it can use a partition-aware client library that routes the request directly to the appropriate node.
Right, exactly. Okay. So he also talks about this in 6.4. I think maybe just like talking about what they learned. But right. So let's say let me just remind myself about what they're saying in this place. Give me a sec. Any storage and yeah, so there's two strategies. Partition aware client. Advantage of the first approach is that the client does not have to think about code specifics to Dynamo. Yes. So it feels like you can choose what you want here, but okay. A node handling a read or write operation is known as the coordinator. Typically, this is the first among the top n nodes in the preference list.
Mm-hmm.
If the requests are received through a load balancer, requests to access a key may be routed to any random node in the ring.
Mm-hmm.
In this scenario, the node that receives the request will not coordinate it if the node is not in the top n of the requested key's preference list.
Mm-hmm.
Instead, that node will forward the request to the first among the top n nodes in the preference list. Read and write operations involve the first n healthy nodes in the preference list, skipping over those that are down or inaccessible. When nodes are healthy, the top n nodes, da, da, da. All right. So I think what I understand from this is it does eventually forward to. So there's a preference list, and I assume the preference list, I'm not sure how the preference is generated, but I know that at least the preference list includes all of the nodes that store the nodes as replicas.
Yeah.
And but I think it can be more than that. But at least we know all the nodes that store nodes as replicas. If so, it's saying that if a read request is received through a
I
load
think,
balancer, it forwards it to, yeah, sorry, go on.
yeah, I think like what I was saying was on track because like the paper said, the node that gets the request first might not necessarily be the coordinator node if that node is not on the
On the preference
preference
list.
list. Yeah.
So if the node is on the
So
preference list, does it still forward it to the
no, it would just replicate it. It would, okay, so if it's a read, then it's not replicating, sorry. So it would just like return the request, the response.
I see. Okay,
Yeah. So
cool.
that's, I guess that's why like having a partition where clients would take out the layer of the load balancer, giving it to any node, then that node now figuring out
What
which
happens?
partition is responsible for this. But in a scenario where it's a naive client that doesn't know like the partitioning structure of the system, then it would just send it to the load balancer. Load balancer will send it to any free node. So now that free node goes through the preference list of that key that it can generate or it even has stored. I think the nodes kind of store like a state of the system at every given point in time. So the node that gets the request first goes through the preference list of the key and sends it to the first node on that preference list. So now
Mhm.
this is the node that actually stores that key. So it's a read, right? So that key will just return the response, so the data item of that key
If
to
it's R1.
directly, if it's R1, right? If it's R1, yes, it will return it to the client. But if it's not R1, then I'm guessing it would so I'm guessing that from
Hmm.
that's where it's tricky. It's either that it's from the first node that gets it from the load balancer. Because R is 2, then it's sending the read to 2, like the
Yeah,
first
like
two
that. That's
nodes on the
exactly so.
preference list.
So what I'm confused about is this can like be drawn in two ways, right? Like which you were describing. So load balancer to a random
Mm.
node to preference list node. Does preference list node now send to? So let's say I want to read from three. So R is equal to 3. So I want to read from 3 nodes. Does preference list node now send to 2 other nodes? Or does the random node that knows about the preference list send to 3 preference
To
list
R nodes
nodes?
of N,
So it
yeah.
gets a request. Also, if like I move from random node to preference list node, and preference list is not the one making the request, and if the request now return to preference list, does preference list send the request directly to the client, or does it send it to random nodes? Sorry, does that make sense? Like,
Yeah, no, I think it sends it directly to the client. I don't see how it would make sense sending back to the random node because all nodes have access to the client. All nodes are equal.
right,
So
and the client should,
from
I
that
mean,
point,
yeah, the client will have an address, and the request will have an
yeah,
ID, and so on. Okay, cool. Yeah, that makes sense.
yeah. So I guess for a read, it's simpler. And even if like R was more than one, R was 3, I think from the first random node that gets it, it would send it to R number of nodes out of the N nodes in the preference list. So it will send it to
Yeah, but like the way the paper talks about
2
this,
out of 3 or something. Hmm.
it says, for example, that it always sends to the. Sorry, give me a sec. It says in this scenario, the node that receives the request will not coordinate if it is not the node in the top n. Instead, the node will forward the request to the first among the top n. So I think that that node now becomes the coordinator. That node now becomes the one that's like, because the coordinator is the one that handles the read. So any node that handles the read or writes is the
This
coordinator.
coordinator. Okay. So we're saying that node now sends the
Yeah.
now
So
basically like replicates the request on the other like
yeah, I
read
think
nodes.
that's what that means. But
Okay.
I don't know, we'll see. But yeah,
Yeah.
okay, cool. That helps. That helps me think about everything together. Thanks for that. I can try writes. You said that reads are simple. I think reads are the ones that are more complicated because I think it's on the reads you do.
Yeah. Conflict
I mean,
resolution, right?
yeah. So you also need to talk about like anti-entropy, which is the how the yeah. So conflict resolution and what do you call this thing? Synchronization between replicas. And it's also on reads they do the synchro. So if like the coordinator node that is sending the so for example in the read path we said that we'll forward the request to a node in the preferences, which becomes the coordinator node. If that coordinator node now sends requests to another server, so it sends to like whatever number of servers it needs to send to, eventually the servers will return their request to coordinator node, even if the coordinator node doesn't wait for everybody. So let's say coordinator node sends to 10 because it knows about 10 nodes on the preference list. It only needs to, oh, okay, remember as well, it sends to all the nodes on the preference list,
True. Yes.
not just
Not
X
just
nodes.
our
So
number of
the
nodes, yeah.
exactly. So it just waits for the first R to
To
respond and
respond.
then send. So now, if all the nodes eventually respond and coordinator node now sees that, it kind of will see everybody's versions and everybody's states and everybody's yeah. So it knows who is skewed the most and who is skewing and I don't know who's getting there. And it can determine by comparing Merkle trees who needs to be updated. So if it sees that one of the nodes on the preferences is skewed, like is the data is like has deviated, it will just send like an update to it by comparing Merkle trees. And so I want to assume like as part of the response to the node, it the like nodes also share their Merkle trees so that they can compare or something. Or maybe like that can be calculated by somehow. But anyway, as part of the reads, the replicant synchronization happens as well. So
Mhm.
a lot of things are happening on the reads. It's also part of the reads that merge conflicts are done as well. So I think that reads are very, very interesting. For writes,
I'm
I can
wondering
talk.
if,
Sorry.
sorry, yeah, I wanted to figure out the order at which the response is sent and reconciliation or conflict resolution happens. So the coordinator node now receives the response of a read request from its replica nodes, right? And it says that they are different. So does it send this different, like differing versions, all three, let's say there are three differing versions, it sends all three differing versions to the client to, okay, okay, so I guess in like syntactic reconciliation, it would sort it out itself first before sending like a reconciled version to the client.
Yeah.
And how it would do that is like with vector clocks and Merkle trees.
Yeah.
But in
So yeah,
semantic reconciliation, it would just send all the different versions like that's the clients to sort out.
yeah. I think that also the it can be both. It's not just it doesn't have to be one. Like some of the versions can be reconciled syntactically. Some of them need to be reconciled semantically. So I think that it will try to reconcile the ones it can, and this might flatten the number of versions it needs to send back.
Mhm.
And the ones it can't reconcile because it's not very obvious which one comes first, like which one causes the other, so on and so forth. It will just send those back. So it's possible that we have one that just needs to be reconciled with syntactic, one that needs to be reconciled just with semantic, or one that needs both. So yeah. I think it's to try to reconcile what it can and then
Yeah.
send to the client to do that.
And like after the client, after it has sent like what it can to the client and So it's up to the client to do the semantic reconciliation. How
Uh,
does it now get back, the um, reconciled version from a
with
semantic reconciliation?
with a put request.
So it waits till the next put request
Yeah, if
in
you
that
don't
same
put any,
context.
yeah, so the context will tell. So remember, it's sending the get, and the get will also return. That actually reminds me. Does it get return multiple contexts for multiple objects, or does it just return one context with all the all the objects? That is something I'm not sure of. But I know when you're putting, like the way that they describe puts here, you put with a context and a key and an object, and it uses the context to eventually know what new version for this object is. Like it knows it's based on the key. It's kind of the same key that you got. Okay, actually, yes, it doesn't need to send multiple contexts. So it knows the key, and it was the same key you got before. It knows what the new context of the key is. Within that context, it knows what the new version is. It knows what you've chosen. So it uses that to kind of decide, I think.
That's interesting. I'm thinking that like between the time when it finishes like the gets and sends like a response with different um a response with different versions, right?
Hmm.
Like it has to wait till it puts by that same it puts with that same context. It has to wait till it puts with that same key and context happens to update its own like version. But if another gets from another like I guess okay, so the if another get happens, that's why I'm thinking like it would still return like an outdated version because like it put hasn't happened yet to update it.
Yeah. Yeah, exactly. I think that it's possible for the versions to, it's also possible for there to be more concurrent writes during this process so that there are even more versions, like versions to reconcile. It's possible. And it's possible for like the number of versions to grow and keep growing, and that becomes an issue. So, but like I think what the paper says is that they never see like based on the implementation, they never see like more than, was it one version or two at like most of the time. Like they never see like this thing um go out of order.
Yeah.
So somehow the system seems to be able to quickly resolve these things and keep versions in check. Yeah.
Fair enough. Okay, so we just finished talking about the life cycle of a read where no failure happens, right?
I think we talked about the failures. So the failures would be I mean, yes, we talked about some parts of failures.
The
So we talked about
failures, yeah.
like the merge conflicts. We talked about the synchronizations that need to happen, and the reason why those would be needed is because of one, failures, two, like just delays in propagation.
Okay.
But if a read fails, like it can like you can't access any server on the preference list, I think you might have a bigger issue than
Yeah,
than
but
with.
but that it would be crazy for that to happen.
Yes, it will, because if you have, so the purpose of replication, you kind of have to have a limit at some point. Like you can replicate endlessly, and you know you need to find like a good balance. There's also like cost implications for this. Like the more you're replicating, the more data you're storing. If I'm a client or a customer that uses Dynamo and I want my data to be replicated X times, I need to pay X times whatever the amount for one is. And so I need to think about that. And like these are like practical issues. So it's possible that all the servers that contain your data, all of them break at the same time. I mean, like I guess technically, but it's a very low probability.
Yeah,
Um, it's a very low
because it's
probability.
like as soon as each server breaks, the reshuffling happens where like a new first of all, we haven't talked about hinted handoffs. So if a server breaks, like its data is like kind of like handed off temporarily to like a replica, something like that. Let's go into it.
We can talk about it in the life of a right. So
Okay.
let's see. Let's talk about right. So left over right, think about, I don't know, I want to write a key. I want to write, so I have a key, I want to write, so let's say I have the key is my customer's cart or something, or customer wants cart. And I have like items in there, sorry, I have items in the cart and I want to store it. So it sends this customer key, it sends the what is currently in the cart, it sends the context, right? Then based on what I've chosen, whether it's client coordination, server coordination, I kind of go through what we talked about before. You either just use a load balancer to send to some random node, which forwards to like one of the nodes on the preference list, and then the node starts the write process to. So assuming we choose server coordination, it sends to all the nodes on the preference list, and it waits for W nodes to respond, including itself. So it's so W minus one nodes to respond, and it returns like back to the client. Now, assuming that, and every time you do this right, you're generating for each server is generating its own version of the, sorry, that is, give me a sec. I think when you're doing the writes, I wonder if it is a coordinator that increases the, I think it has to be coordinator. It can't be everybody.
That does what?
Because you write first and then you replicate. I think that's what happens. Yes, you write and replicate. So you write and immediately replicate. So you write the version. So you create a new version. So when you do it right, you make a new version of the write, and then you replicate this write to multiple nodes, and then you wait for the nodes to respond. So you're sending the same version that you've written, because if not, um, yeah, if not, that gets complicated. So you're not,
I wasn't
you're,
actually sure about this because isn't that still introducing a single point of failure where like if it's one node that is still doing the replication, it will replicate whatever like false data it has, or if that node even dies before it's able to replicate, it would be a problem. I was thinking the replication happens to all W nodes, all N nodes rather at a time, and then W responds.
the replication happens to all W nodes. What does W mean? I think W means that so N
Just
means,
N,
N is replication. N
yes,
means like, and W and N and W and R are like, or at least ideally should be
like
within
how many
N.
nodes? Yes, yes.
So I think that, and this might be wrong, but I think that what it means is, because I can't imagine issuing. So what would they do? Like, it's to issue the rights to everybody. Everybody would do their own version of the right and respond back to the coordinator. I think
Yeah.
that potentially what would happen is the coordinator will, um, hmm. Sorry, let me think about this for a sec.
Um, I think you might be right.
I think it's, yeah, I think the first node would do the right, create a new version of the object, and then replicate that. Like, I
Hmm.
think that is what makes sense to me.
Yeah,
But,
yeah, actually.
and it will wait for like n replicas to respond. So I guess like
It waits for W replicas to respond.
W replicas to respond, thank you, before it responds. And if, for example, like some of it doesn't have up to W healthy nodes, this is where hidden handoff comes in, where like it now chooses some other random node outside of N that will, maybe within N, I'm not sure, but I think outside of N, in the preference list, that will store the objects meant for whatever node is down for a limited time.
Mhm.
And when that node comes back up, so I think this node that stores this thing would regularly check um, whether the node has become active. and there'll be a threshold. There has to be a threshold for this because if the node is not active after a while, it needs to assume
Yeah.
that the node is dead. It doesn't really say what happens to the data that is stored temporarily after, but it kind of needs to be removed at some point. So it will wait for WNOS to respond and then send the response back to the client. And yeah, I think that is literally it. So the most it does during the write is it needs to create the vector clock, like when the node makes an edit, which would be the coordinator node to the object. And it needs to wait for n replicas. And within that process, some replicas might not be available. So you might need to do hint and handoff. Um, yeah.
And
So
like hinted handoff means it stores the data with a hint that this data
it's
is not
for,
actually mine or is for this other node.
yeah, exactly.
And I think it doesn't store this in its main storage. I think it stores this in like a local buffer or something like that. I don't know if I read that correctly. A local store.
Mhm. This
Yeah,
can mean anything. Like just RAM, but like another variable or something. Like it could be anything to be fair. But yeah.
true. Okay. Okay. So we finished for it, right? Okay. Uh, I
I
think
think we've covered.
that simplifies things.
Yeah,
Yeah.
I like the life cycle thing. It helps.
Hmm.
So I wonder, like, I don't think there's anything else we haven't talked about. Or is there something you think we should talk about before we go?
Yeah, I feel like we can just talk about things from our perspective, not necessarily like what's in the paper. So something I was
Hmm.
wondering was like how, so you see the paper or Dynamo like prioritizes availability over consistency. What does
Yep.
this look like in like other applications? Like, do you know any other application that does this? And what does that look like?
Um, One I know is like Instagram. Before Instagram, remove all the likes. You could like check different instances of your account and see like different amount of likes for.
Really?
And I think it still happens on Twitter maybe. Like if you open, it kind of gets obscured because especially for people who have like thousands of likes, it kind of gets obscured because for example 3.6K, right, would just be the number there, but it might actually be 3.601 or 3.623 or something. Like so it kind of, if the system gets eventually consistent quick enough, like it gets obscured very, very quickly. So it's easy to miss it. But I think Twitter, for example, I would assume that the likes are eventually consistent. I don't see how like that can be like a synchronous thing. It would not, it
Yeah.
doesn't seem scalable. So Instagram likes also kind of come to mind. Um, what else?
I feel like chat applications that I've used a couple where like the last message I'm seeing is not the last message you're seeing. Like,
Hmm.
yeah, because the whole point of consistency is that from every viewpoint of the system, we are seeing the same states, like the same thing. But
Yeah.
like, yeah, in some chat apps, it's like I sent my message first, you sent yours second, but I'm seeing yours first and mine second, and you are seeing mine, yeah, the other
Yeah,
way.
it happens a lot. Yes, 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 yes. And I think like for it's it's probably better for like the chat application to be available than for it to like be like, oh yeah, this is unavailable right now because we've not yet synced all the chats. I
Mm,
think that, for example, what happens sometimes, even like when you have these skews, is that eventually the messages might get rearranged by the application. So even if, for example, I'm seeing like I post a message and I see like someone else's reply come first, but I'm like, that doesn't make sense. And sometimes when I go back, it's been rearranged by the application. So in that way, like, the application is doing their own conflict resolution there. But yeah, like a chat application seems like also like a good place where eventual consistency is important. So
yeah, definitely not like not as great in like a banking app or like a healthcare system.
yeah, yeah. So you don't want eventual consistency for some things in the banking app. Like if my transaction is not going to succeed, I want it to fail immediately. I don't want you to tell me that it to be virtually consistent. Like, no, fail it, please. Although, so the way some banking systems work, that's actually how it works. Like
Yeah,
they,
like I was literally about to say that.
like settlements,
Exactly.
like n+1 settlements, where n is like the days. Like settlements in even Nigeria, I think for the companies, I think settlements happen like n+1. I think some people offer same day settlements, but even that is still like not immediate. It's like at the end of the day, you reconcile everything and you make sure you actually have the money. So what people usually have to do, they have to either cover it. So they usually will cover it with their own money, so that they assume that this money is here, so they cover it. Um, and yeah, like even in banking applications, I think eventual consistency is a thing because it's just like a lot of moving parts. A lot of people need to work together. Sometimes there are even manual processes in between these things where like moving money from one country, for example, to another has a lot of like manual steps sometimes. Like some people have to manually review stuff. So even in money systems, it's there, to be
I
fair.
feel like that's a feature. Like it's expected that it is that way. It's like a defined process for it to be that way. But
Mm.
if it was happening like irregularly and like in places where it's not supposed to happen, I'm trying to think of like the example you gave, like no, let's see. Like okay, for instance, the money in my like my balance, the balance I'm seeing should always be accurate
Yeah.
because I don't want to think I have 100K, but actually I have 50K, and then I now transfer like 75K.
But even that's what I'm saying, even that is fine. So sometimes, like that sometimes people know that they don't have up to
What they're
100K in their
saying is
account.
no money.
They know that they spend this amount, but they go and they want to try and transfer. Now, for example, where the bank can be smart and do like like make sure that this data is accurate is at the point of the transfer. Like so they might eventually update what the user is seeing. Or sometimes if the user like some apps, if you like, I don't know, press a refresh button, like pull down your screen something, it like makes a synchronous request to get your balance and it pulls it from the right places. But if you've not done that, like it just kind of stays and maybe updates over time. But at the point of doing the transaction, the like a process in their system can check what your actual balance is, or has to. It has to check and it has to know. And if it
Yeah,
cannot find out, it has to fail that transaction. Like if some
exactly.
systems are down and you don't have you have to fail it. So that is one place where they need to prioritize consistency at the point of transacting. 'Cause whatever they allow, like there's a whole process for if you want to dispute it, it's a whole thing. It's like
Yeah,
yeah,
yeah, definitely the one that's in when it
yeah.
comes to money. Okay. I guess we've covered a lot. Was there anything that like jumped out to you when you were reading the paper? Something really shocking.
Not shocking. That's really interesting. I liked a lot of how they combined stuff. Um, and yeah, reading the paper kind of makes me interested in reading more papers. I guess I've read papers before, but I found this one very interesting. I read it a lot of times. I made a lot of notes. So it was really cool to see them apply and also see the results of all the stuff that they did. Um, I don't think they went into details about every single thing they did, but they did talk about a lot, and they also talked about what the impact was. So it was great to see um, like this actually working in production. I'm sure it was like revolutionary at the time. Now we kind of see a lot of systems use these
Yeah,
concepts anyway, but yeah, it was great to see.
I
What
think
about
for
you? Yeah.
for me there were lots of things that were pretty shocking. I guess cause not shocking, but like they were new to me and interesting to see that oh like this actually exists. Cause I'm not really like I haven't well I guess I haven't like read a lot about like SRE systems and how like like systems handle availability and things like this. So this was
Hmm.
like kind of like an introduction in a lot of ways to those concepts, but also like how they extra like innovative things they did even within those concepts. So that was
Yeah.
pretty cool. And I liked that they talked about like the different data structures they used. It made it more like real, like they actually built this thing. It's not just an abstract concept. So like
Mhm.
trees, for instance, is something that I'll probably try to implement on my own and see like really see how it works. I guess
Yeah.
also vector clocks, because those were also just like lists of node counter pairs and yeah, so
It's a
I
cool
think
name.
that
Is a
right.
cool name for a tuple. Is I like the name. It's just a tuple though. It's like a list of
Yeah.
tuples,
Hmm.
but nice name. I like
TikTok,
it.
like why? Oh yeah, yeah. I think this was a pretty cool episode.
Yeah, I'm glad we finally did this, and I think it was definitely like a very important learning experience for me. So yeah, thank you very much for hosting and asking and discussing.
Yeah, and thank you for explaining a lot.
Yeah. All right.
All right. Bye.
Bye. See you next time.
Yep.